Hello, this is Dr. J, and I'm going to provide an introduction to the finite impulse response, or FIR filters. The finite impulse response filters, or FIR filters, are a special class of digital filters. Digital filters consist mostly of three basic components. They are the adders, scalar multipliers, and the time delays. The time delays determine the order of the filter, while scalar multipliers determines the type of filters. And how to choose these values for these multipliers, the scalar multipliers, is what makes it magic in terms of building digital filters such as high pass, low pass, band reject filters. They provide more flexibility than analog filters because if you want to change the frequency response of analog filters, you need to unsolder either a resistor, capacitor, or inductor, and that takes time and labor to change the specifications of an analog filters. Whereas digital filters, you can change the order or the scalar multipliers. You may want to reduce the order because it may take processing time, and that's a disadvantage of digital filters, whereas analog filters are pretty instantaneous. Okay, the finite impulse response filter is basically a feed-forward filter. In other words, you take the inputs to the filter and feed it forward to generate an output. And this is called the finite differential equation, which is in parallel with a differential equation found in continuous systems. Here we have an output sample, which is a weighted sum of input samples. And here the unit impulse response is used to completely characterize the digital filter or system. And important concepts of linearity and time invariance is used to help determine what the output of the digital filter is. Let me just give you a quick info on the infinite impulse response, which I'll discuss in more detail in future videos. But unlike the FIR filter, which has a finite length of its impulse response, the IIR filter could have an infinite impulse response. And basically, its output consists of a combination of feed-forward inputs and feedback outputs. So you're taking the output and feeding back as part of the input along with the signal input. Examples of IIR filters include the Butterworth, the Chebyshev, and the elliptic filters. And I'll discuss these in future videos. So let's take a look at discrete time signals. Basically, we want to take an input, which is basically a sequence of numbers, and we want to take that input and manipulate or operate on it such that we get an output sequence with desirable properties. For example, getting rid of noise. So the output sequence is related to the input sequence by some operation T. So for example, the T operation is just taking the input sequence and multiplying it by 5. Or taking a combination of the present input, and in this case these past two inputs, and average them out to form basically a sliding window or moving average filter. So in this example, this filter is just basically performing the function of a running or moving average, and it depends on three consecutive input values shown here. So X represents our input and Y represents Okay, let me give you a visual of a discrete time filter and see what it does. So here what we have is a discrete time system or filter. LTI stands for linear time invariance. I'll talk about this in future videos. And we see that the discrete time impulse of input completely describes this filter. So what we have is an input sequence described by X sub n and an output sequence described by Y sub n. Y sub n is related with the input sequence through some operation T that I talked about earlier. I give you some examples. So this is what we mean by a discrete time filter. It takes some input, manipulates the input to give you some desired output. So this input may have contained noise, and what this filter does is gets rid of that noise to give you some output sequence that has some desirable properties. So here we have an output sequence xn. We have this filter descriptions. How we select these coefficients of these numbers at the various places in time, okay, is used to give us a desired output. So this is basically a pictorial view of what a discrete time filter is, and in our case, our focus would be a finite impulse response filter, or FIR filter. We're going to do a simple FIR filter that performs a running average. So here we have this input sequence, and we're going to manipulate this input sequence to give us some certain output. First of all, it has a finite interval from 0 to 5, so this is why it's called has a finite length, this sequence. It goes from 0 to 5, as shown here. X0 consists of value of 3, X1 consists of value of 2, and X2 consists of a value of 1. So that's what we have here in this set. We're going to take the output of these three numbers, add them all up, and take the average of them. So we just add 3, 2, and 1 is 6 divided by 3, and that gives us a 2. The index we used here, and can be arbitrary, is 0. So for corresponding n of 0, we have an output of 2. Here, we'll do another example. We'll find y1. In this case, we need the values of 2, 1, and 2 corresponding to this set. So 2, 1, and 2, performing our averaging. 2 plus 1 plus 2 is 5, so we have a result for y1 of 5/3. And again, this running average is also known as a sliding window of fixed length 3 right here. Now you can represent this moving average as follows by performing this operation for y0. And this is what we did before in the previous slide. And for y1, 1/3 x1 plus x2 plus x3, giving us a value of y1 of 2. Now in general, we can represent this running average as follows, where we have xn, xn plus 1, xn plus 2. So we have the present value plus 2 future values. Again, these 2 future values, when we use future values to give us the output, we call that a non-causal system. This running average equation here is also known as a difference equation, and it serves the same purpose as a differential equation. In other words, we don't want the output to appear before the input, and that's what is meant by in this case, the difference equation serves to describe the dynamics of a digital filter system for discrete time systems. In the next video, I'll talk about what we mean by causal and non-causal systems in terms of past, present, and future values of the input signal. Signing off is Dr. J.